Good morning. So today in this tutorial, today I will talk about chapter 2. In the chapter 1, what we did is um, we explained all the figures one by one, and in the entire tutorial we will have 10 lecture series, and in each lecture I will uh, concentrate only on the figures primarily, and the chart and tables, so that you can easily uh, look at the pictures, and then easily put in your mind what the concept is. Because if you go through the text, then in the text there are mathematical equations, and then you need a background, very good research background, to understand what is going on. But this tutorial is meant for those who have purchased the book and then have told me that they are finding it very difficult to go through, because they need to get back to Google, read in Wikipedia or Google search, read an article, learn about the basic definitions of terms, and then they need to come back and then read the book again. And then the problem is, one person is expert in mathematics, one person is expert in biology, one person is expert in um, in quantum mechanics, some people in mathematics, some people in material science. So like material science is exclusively in chapter 9. So until you go to chapter 9, you can't fathom. The biology starts and ends in chapter 5. And so so what do we do? Or chapter 6. Chapter 6 is actually exclusively biology. And then brain science, those who are working in chapter 7 only. Then if you are working on photonics, optical vortex, and magnetic technologies for circuit element or memory store or that kind of devices, then it's only in chapter 8. So what happens is, many different kind of expertise is essential to get into the book. And then what I'm doing is telling the very basic concepts in simple language in all the figures. So what happens, if you have the book and if you go through this tutorial, you can understand what we are talking about, and then you can make some sense. Then you can look at the text and then avoid the equations, and then look at the conclusions made. And then if there are technical words, you can bypass. So let's begin the journey through chapter 2. So in the chapter 2, the title of the chapter 2 is replacing Turing tape with a fractal tape, fractal information theory and geometric musical language. As I said in our first video, first tutorial part, that where I explained the chapter 1, that one of the key feature of the new kind of artificial brain that we want to build is that we need to come up with a new information theory. Why? Because because in the Turing philosophy, we considered that every single event, whatever is happening in the universe, should happen one after another in a sequential manner. And what we are considering, that events happen within and above. So it's a vertical journey that mankind never made. And we want to make a vertical journey. That's why every single field we need to contribute and start from scratch. That's why the book becomes difficult. So in the chapter 2, we exclusively discuss only the information theory, which you know very well for the last 80, 90 years or 100 years. Our computer is built based on the Shannon's entropy, and then Shannon's information theory, and all this kind of things. So people also talk about quantum information theory, but that is basically the same like the normal information theory. So why is it different? So what we do is we try to put say 15 geometric shapes, basic geometric shapes, like the Platonic geometries. You know that only few geometric shapes are there, and those you can repeat and combine to create every single possible other geometries of the universe. In solid state physics, if you had solid state physics, then you have read that only 22 Bravais lattices are there. So only few symmetries are there. And then with that, every single material that you see in front of us could be explained. So this kind of things we have already already known. So now what we are doing is, if you start with incompleteness of current information theory in the section 2.1, that is the first part of the book. So here I have started the chapter asking that if I say 1 0 0 0 0 0 1 0 1 0 1 0 1 0 1 0 0 0 0 0, does it make any sense? So in your machine, actually, this kind of things are there. New kind of information theory, what we want to do is there will be only geometric shapes, 15 geometric shapes, just like you have 26 letters in English language, or any language. You have finite number of letters with which you can you construct a word, and then you construct sentence, and you construct argument. Similarly, here there will be geometric shapes, and the geometric shapes will be combined. And how do we combine? We take the ratio of the sides of the geometric shapes, their angle, and then we shift them to actually vary the information content. So basically we have the geometric shapes, and we will deform the geometric shapes to write the information content. So there will be no equation in the new kind of information theory that we are talking about, and geometric shapes will change, and then each corner of the geometric shape could be the singularity point, where we will put other geometric shape inside. Suppose you have a cube. In the cube we will put inside. So that is the kind of thing that where we are trying to approach. So we are saying that in the existing information theory, it doesn't make any sense to you because it's a bit, and it does not have any character. And then a human imagines something and then assigns a value to it. But when we say geometric shape, it's already an event. So if we have a clock, and inside the sphere, I put a cube, and then a clock is rotating and then touching the corner points, then it is an event, it is an information, it has a physical significance, everything. So the importance of human we are trying to avoid. Okay, so one word that I am getting lots of question is singularity. So many people are asking, what is singularity? Singularity is like a yesterday I explained in the tutorial of chapter 1. I'm explaining again, because singularity is a term that you will get many points in the many concepts in this book. And then singularity is simply, suppose you have one clock and you have another clock. Both the clock are interacting with each other, and then due to destructive interference at some path, some point on the phase evolution of when it is rotating in the circle, some point you find that you cannot define whether it is on the circle or outside the circle. So it is undefined. It is not zero. Zero is a finite value. So when you cannot say that what is the value here, because both overlapped, and then they create a situation that your state belongs to this circle or that circle, or this clock to that clock, you can't determine. That is the point. So that is singularity. And what is the physical significance of singularity? For an example, if you have, it's Maharshi Gautama argued about Sandeha, confusion, and then the Hindu way of making a decision was, you do not try to find facts, just like in the current information theory, you try to find facts. So what you do is you search for the truth, and then get many truth, and then from truth you combine them with your imagination, and then you build how the universe would be, because you create a structure of facts connecting them together, and then you try to fit it with the observation that you made with the experiment in nature, and then you try to modify this architecture of fact. That is what you do in current science, or in the current computation. And people think that this particular concept is enough to understand human brain. We say absolutely not. What we say is what for 3,000 years Hindus have been doing in India. So what they do is they go for Confucian. Confucian, they very well define. Many hundreds of schools were there, and they were fighting with each other for thousands of years, and then some people believe in this kind of schools and some people believe in other kind of schools. What do they do is they try to find that, suppose you see a problem. When you see a problem, what you will do is you will try to find what is the most important thing that you don't know. Okay, and you have multiple solutions which are equally probable almost. This can happen, that can also happen, that can also happen, that can happen. If you find 3 or 4, then 3 is triangle, 4 is a square. So you take a circle and put draw a square, and you put one confusion, second, 3, 4, 4 choices. So whole circle is a confusion, and you have 4 options. But you go to one option, and then you find even with that one also you are not very sure. So you go inside and you find some other geometric shapes and some other confusions inside. So in this way, you go on creating the architecture of confusion. You continue to do this until you reach a point when you have only facts. You do not find any confusion at all. Then this architecture of confusion is the solution of the problem. So you never try to, I have discussed Wheeler's paper, Eat from Bit. It is a very famous paper where he said that when you actually collect the bits or small truths, yes, no answers, and then use human imagination to solve it, then you are never able to get into things. It is always human imagination. So you can't do it. So what Hindus have been suggesting is that go for architecture of confusion. So confusion is just like singularity, but confusion is very well and very scientifically defined. If you translate the hymns, you will find that cognitive or non-cognitive option possibilities that encounter in a human mind with equal or multiple probabilities. In this kind of situation, you can consider that particular factor as a confusion or singularity. So we try to do a similar thing here. So in the first page, you will find that I have already started talking it from bit, and then this was a very interesting point of debate, because Wheeler started challenging the way we were doing science, it from bit, in the 1960s, 70s, 80s. He had many research papers, and many people contributed that the way we were doing science, whether it is right or not. And then Wheeler's it from bit, or this kind of philosophy, where is actually throughout this book. So you will find it many times. It is coming. So we come to figure 2.1, and it is page 26 actually. And here you will find that why we are saying that the current information theory is incomplete, primarily inspired by it from bit theorem of Wheeler, but there are human artificial intelligence predicting future, and then information. Information is actually a statement where you observe something with your own bias, and then what you do is, when you fit the what is happening in nature with your own model, you try to find supporters that and supporters will follow your path, ask the same question to nature in the same way that you have done it, and then he will say that, okay, if I follow your question, ask the question to nature in your own way, then I will see what you have seen. And that is called reproducibility, and that is how scientific theory is established. So this is has been the world of Turing and Gödel, and then where logic is supreme, and then information goes on, and predicting future is nothing but what you do is you look at certain things, and then you combine those events, and you try to repeat that what has happened many times and predict the future. So that is going to change forever in this book, in this new information theory, because in this new information theory, we are going to bring in new factors when we get into the information architecture. So in artificial intelligence also, you try to mimic and what humans are doing, and then you call it and you put human instructions. I mean, mostly the software programmers' instructions, and you call it artificial intelligence. So all these are not right, are not the proper natural intelligence that we have in our brain. I mean, when we when we meet with some person, we absolutely have no idea. We go on for a completely different considerations, and then we still survive. So, so yes and no bits, and then the problem associated with the bits or looking into the universe as a sequential world, and there are problems. So we have discussed it, page 26, 27, and it continues. I mean, many different kind of aspects came historically challenging this particular aspect. On page 28, actually, we proposed why in 2014 we came up with fractal tape. So defining fractal tape is very easy, very simple. What you do is, Turing tape. Turing tape is an infinite tape, as I explained in tutorial 1. There are two gods. One god is rolling out new tape, and another god is rolling back. So each the tape has many cells in linear fashion, and then they have 0 1 0 1, yes or no answers. Now if you define a new kind of tape where each cell contains another similar tape inside, then Turing philosophy falls apart, because your journey is endless and ad infinitum everywhere. I mean, you can never end. Then won't that tape be useless? How do we use that tape? So that will come in chapter 3. But if that is the case, then we reach singularity point, because each cell becomes undefined. You can't say what is the state of a cell, or Turing tape, each cell of a Turing tape, or the modified Turing tape that we are talking about. So we will call it fractal tape. Fractal tape. Fractal word is again very confusing in this book, because we take pattern of primes. Primes never repeat. We take pattern of primes, but there are apparent self-similarity in the distribution of primes and its compositions. So that apparent self-similarity, due to that apparent self-similarity, we have used the word fractal tape, but in the true sense, it is never a fractal, because primes in an absolute fashion never repeats. Certain features repeat, but new features of repetitions come up. So even after the next 1,000 years, you will find some mathematicians would discover some new patterns in some new kind of primes. So the invention will be endless. So what happens is, actually, when we define the cell, each element of the cell will be a geometric shape. Then, and inside each corner of that geometric shape, there will be more geometric shape. When we'll define it, then we will go for a fractal tape. So from there onwards, actually, we come to figure 2.2. Figure 2.2 is actually a very important figure, where we make a transition from the old information theory. If you look at figure top right part of the figure 2.2, you will find that we have said 0 1, and in quantum you have a Bloch sphere, and then at the bottom you have a one real point and top one real point, that is 0 and 1, and those are classical points. So all others are imaginary. Now when we take our information theory, the top and the bottom or points doesn't exist. There is no classical point. What you get is, along the equator of this fate sphere, you find it's a triangle or square or pentagon, or you can put even a 3D shape inside this fate sphere. So you will have multiple points. Corners are touching the surface of the sphere, and there those corners are singularity points. Those are undefined points. So it's a journey to singularity. So those undefined points, if you enter inside, you will find a new geometric shape. So that is actually explained in figure 2.2b. You take a pentagon and then you find something is written pole equal to bing. So basically burst. And then you go to the corner and you find some new geometric shape, and you go inside and you find more geometric shapes, and the journey continues. You can't stop it. So so from one geometric shape you go to the very complex architectures. If you go inside and inside and inside, just below that series of geometric shapes, you will find fate spheres representation of the same. So fate sphere, what is fate sphere? Fate sphere is suppose you have two choices, and then from one choice to another choice you can go by infinite possible paths, one to another. That is called fate sphere, to be very simple. And in our case, we do not have classical points, we have singularity points. So from one singularity point to another singularity point, you can move through many different pathways. Okay, so that is the significance of the fate sphere. Now, what if you look at the pictures, it's very nice. So what you do is you have, say, 3 points. I always talk about triangle because it's the simplest geometric shape that covers a space. So if you have a sphere and then 3 points in just like a triangle, now what happens is you slice it off in the fate sphere, and then you insert another sphere, guest sphere on the host sphere. So these guest spheres, after slicing it off, when you put it, another fate sphere comes in and another clock actually starts. So if this is a sphere and then one sphere, you find one clock here, another clock here, another clock here, new sphere gets in. And then on that sphere becomes guest, and that becomes a host, and then it takes some smaller spheres, and then you go on and on and on and on. The journey is continuous. So earlier, what happened when you had a bit, or you had one phase sphere in quantum, what you used to do, you used to create the entire circuit, and the entire circuit, when you have entangled state, then you have 0 and 1. So collapse, that means either distribution of 0 1 1 0 0 0 0 1 1 1 1 1 and collapse, and then you get the solution of the problem. But in this case, when you have this kind of information architecture, which is endless journey inside the fate sphere, in any direction you go, up, above, down, wherever you go, then what happens is transition of the fate sphere. For an example, you are looking for a particular direction, you are seeing, okay, the fate sphere looks like this. You are going from a different part, you find a different kind of answers. And then if you look at from the top at the bottom region, okay, so the whole pattern, you see something, and the other person would also see something, and those will be similar. So now here, harvesting the topology, enjoying how the topology looks like, is kind of solution of the problem. And as I said, that architecture of confusion we will build. And what is at the bottom of this temple-like architecture of confusion is that facts, because you end with facts, fact, and then confusion to the top, and then on the top you have only one confusion. So this is the architecture we built, and then this is the figure 2.2b, is the kind of spherical phase representation of how that information would look like. Now this is the engineering of the block sphere. Now we come to self-assembly of this spheres. How do they do it? So basically figure 2.3 is the same thing that was shown in figure 2.2b, but here we have shown it or explained it with much more clarity, because many people, when we explain this information theory to them, they say, oh, so triangle is your unit of information. No, that's why figure 2.3a, we have triangle. We started from triangle and then sliced it off and put guest spheres, fate spheres, and then more guest spheres, and then in the bottom row of figure 2.3a, we started from square and did the same thing. So this is just to tell the readers that do not say that only one kind of geometry. You can start from any kind of geometry. You can start from 3D shape, and then you can go on and on and on. So and then there is a shadow. Big shadow means confusion, or you don't know what it is, or the singularity point. So whole geometric architecture is a singularity point. And then you understand that when you have entire information, it's a very complex sphere, which are clock architecture of clock. And nowhere there is reality. So how do you get reality? Because you are also an architecture of clock. So you try to match your architecture of clock with the architecture of clock that you want to read. And then there is an interaction, and then the interaction output is what you perceive. Okay. So here your imagination that was in the old information theory, your imagination had a supreme value, and it from bit ideas were supreme value. Your imagination get very much restricted, because if geometric shapes are there, how do you put the geometric shapes? How do you arrange? How do you change the symmetries, break the symmetries? All those are very well defined mathematically. So once you get into the world of geometric shapes and topology and other kind of things, it's not very independent. So you can't do anything. After a certain period of time, everything will be taken over. Basically, that's what we want. We want free will to go away. We want to get into the world of topology and geometric shapes and spontaneous transition, change of the geometric shapes by themselves, so that we can create an artificial brain. We can create a conscious machine, a machine that will decide by itself. Now, consciousness word is debatable. Don't get into, whenever you see consciousness word in this book, don't get too much into the definition of what is consciousness. Consciousness we have defined as a way by which a particular hardware operates by itself. It doesn't need to take any information from the universe, but it can think, and it can create many things. It can simulate all the possibilities of the universe by itself. So that's kind of the kind of definition that we consider. Now, as the time will pass by, you can make this definition much more complex. Then it will become much more harder and harder problem. That is not the objective here. This is the first book where we are trying to introduce a new way to understand human consciousness, and then realize it experimentally, because the whole book, every single thing that we have written in the book is experimentally realized in the lab, and after that we have written it. There is no speculation or certain things. If that happens, then that will happen. No. Everything is written clearly, straightforward manner. So you can basically reject the whole hypothesis, whole proposal by disproving with new experimental facts and edit it. So one difference with other researchers is that there is not much story here. What we have realized is what we have said. So if you go to figure 2.3b, what we have done is, mathematically we have introduced tensor a little bit. Tensor is nothing but matrix. It's just like you have a grid-like structure. So those who don't know what is tensor or matrix, it's a grid-like structure, and you have lot of values. Okay, and those values represent the event or situation. How do they do it? What happens is, in the grid you write the values, and then in the vertical column in the left and the top horizontal column, these two corresponding elements actually interact. So you go down from particular rank element bottom, and particular rank element horizontally, and you reach at a particular point. So these two factors are responsible for the outcome here. So they two will interact, and this will be the output. Okay, so with this tensor or this grid, what do we write in this tensor? We write the information of how big is the singularity, what is the location of the singularity on the phase sphere, and then the diameter, and then the clock is rotating, then how the clock is rotating, what is the speed of the clock. The speed of the clock is actually represented with the diameter. So basically everything we convert into geometric shape. And then why do we do that? Because geometric shape change then would alone represent what is the solution of a problem. So here you see that at very elementary level, 2 by 2 tensor, how can we create? Okay, so we write what are the singularity points, that details. So you can see that there is a spike, and if there is a spike in the response of a matter, when you pump a signal, you'll find that as the frequency changes, at a certain frequency, pop, there is a jump, and then that actually is the singularity point. So you can basically measure it, pump a signal, and then it boom, it bursts, and then that is you write as a singularity point. So so this is all about figure 2.3, and then we will go to figure 2.4. In the figure 2.4, in the top, you can see that we have taken a pair of DNA based structures, because DNA based structures are widely studied for computation. People believe that by combining DNA, they can solve complex problems very easily, and there are many people who believe in it. So here we are doing something very different. We are taking the geometric shape that is produced by, say, DNA self-assembly, and then if we convert it into geometric shapes, into phase sphere, how would it look like, and how would we convert that into a tensor? So that we have shown here. So basically, what you can do is when you see the clocks, you can assign I, J, K, say quaternion. You are taking a quaternion, 4 by 4 matrix or tensor. What is that? 4 by 4 grid. When you were a young kid, then you used to get a grid based page where you used to put coordinates. Okay, so here also just the similar kind of thing. You just go through different imaginary world, say 1, I, J, K. So I is one imaginary world, J is another imaginary world, K is another imaginary world. So how do we get the concept of imaginary world? For an example, a plus ib whole square is equal to a square minus b square plus 2iab. So minus b square term comes from the imaginary world to the reality, a square minus b square. Okay, so when you take a whole square, so what happens? This imaginary world I square equal to minus 1. Now you can have 12 imaginary world, then sum of the squares of all those I, J, K, L, M, N, O, P, Q, R of all these 12 terms would be 1. So we have said that in the last in the figure 1.8 in chapter 1, and here also you find the 3 imaginary world and 1 real world. Real world is 1 and imaginary worlds are I, J, K. So it's called quaternions. So this is known for the last 200 years. So you can represent that, okay, this clock goes to that imaginary world, that clock goes to that imaginary world. But how do I decide which clock goes to which imaginary world? Looking at the DNA structure or any particular object, say there is a statue of a king, and then which part will go where? It depends on the interactions that they have. Okay, for an example, I and J, if they interact, the K, other imaginary world, gets affected. So if this component and this component interact and that component get affected, then we bring them together in the tensor and then we put in this form. So basically, this is a beautiful journey from an object, a dynamic object, to the tensor that we have tried to make understand. And then below that is the famous frog. Everybody tells me that they are tired looking at my frog. So this frog, actually, we put different circles and then we convert it into a phase sphere. So different organs interact and then other organs get affected. And if you see that organ moves, then that organ goes up, is changing. So based on that, actually, you can create the phase spheres. Okay, so you take one sphere and then you put leg here. Okay, eyes would be here as a sphere. So everything comes, all the components come as a sphere. So figure 2.4b actually have the 15 geometric shapes which we use, and then what we can do is figure 2.4b C, figure 2.4c, you will find that one clock is there and another clock is there. Two clocks are rotating relative to each other and they are generating the geometric shapes. So basically you can physically create those geometric shapes with nested clocks. in chapter 4, we will see that we can do any kind of mathematics just using circles. Okay, so how do we do information processing in this new information theory? That is shown in figure 2.4e. You see there is a cat and there is a dog. So you take the cat, you convert it into nested spheres. Okay, so just like we converted in figure 2.4d, we converted a frog into nested spheres, or nested clocks. Similarly, you convert cat to the nested spheres, and then if you change if there is a subtle change in the clock position, it becomes a dog. So when you retrieve the information, you'll find subtle changes actually converting it into a dog. So this is extremely important. So now you have those who are kind of quite intelligent, you have started feeling that now you know how the information could change. Relative change in the sphere position, relative change in the geometric position can convert one species to another. So basically learning would become extremely easy. Now we have to build time crystal analyzer. So if you go to the next page, which is page 33, you will find that we are introducing time crystal analyzer. What is time crystal analyzer? So until now, you used to do FFT, Fourier transform. That means you send different signals of different frequencies to a particular object, and then the object would reply with the signals of particular frequency, and you take the spectrum at which frequencies they are pumping on. But that Fourier transform, we used to call it. So in the frequencies, which frequency signal the object that we want to measure or understand is returning back. For the first time, we are suggesting to make a change. Instead of getting Fourier transform of the frequencies that is coming up, we take time crystals. What is time crystals? So each peak will shift. If you disturb this particular peak, other peaks will shift. So each peak, actually resonance peak, or where we get the response of frequencies from the object when it comes, then there's a burst of signal, and that burst of signal comes from singularity. This is not proposed by us. This is established many times. We have cited this particular work. There are many such works that whenever you have a singularity point, energy bursts from there. Those are actually emitting points. So time crystal analyzer, what you do is relative. If you disturb one peak, how the other peaks would shift, you find it out and then put them together on a phase sphere. So instead of presenting a spectrum, which spectrum, spectroscopic studies are the fundamentals of characterization in every single research. But we want to change that culture forever. What we want to do is to represent every single system in terms of nested spheres like this. Then you get much more information, and this chapter is exclusively discussing how basic culture of Fourier transform and then spectrum analysis. There are hundreds and hundreds of instruments are there, scientific instruments, which are sold in the market, which you can buy and then do characterization. We are saying that era should be over. So we have patented this particular technology, where you can convert every single information in terms of nested spheres, and when you do that, actually you can get much more information from the system. So imagine you have a multimeter. You can see you put two probe there. You have a multimeter you put in the plant or somewhere, and you see the nested spheres, a hologram of nested spheres, a futuristic machine. Imagine that we can have. So how do we represent them? It's called continued fraction. So you can write in a very nice manner: 1 plus 1 by 1 plus 2 by 1 plus 3 by. In early school days, you have done this kind of 1 by 1 by 1 by 1 by this fractional analysis. This is called continued fraction, and actually you can represent whole sphere inside a sphere inside a sphere with this kind of continued fraction. So there is many different ways you can analyze. We just wanted to give a hint in page 33 how you can get into that. Now we come to the very interesting part, figure 2.5. Figure 2.5 actually tells you how can you generate your own time crystal analyzer. If top part you will find if you have a sphere and one clock is rotating, then it's a sinusoidal wave. You all know about it. But if you have a sphere and then you have a guest sphere on the host sphere, then for certain time you will find that the clock rotates on the host, and then on the guest, and then on the host. Okay, and then the guest can become a host and can have another one. Then what you will find, a big one for bigger host, a smaller one for smaller host, and then the smallest guest, and then the bigger host and the biggest host. Okay, so this is the kind of signal that you see, and looking at the signal you have to build an algorithm. We have built it, and you have to convert it into a nested sphere, a spherical structure. So there are many such examples over there, and one very interesting thing is 2.5b. When you look at this, who is the host, who is the guest, and who is the guest of the guest? How do you determine that? That is not so random. Throughout the book, even in the chapter 10, when we go for the tutorial part 10, we will see that who does it? The host is the smallest, the biggest circle. So is a subject, or who does the work in an English sentence. How do you do it? Is how do you put the argument? Is who does it, at which condition, what it does, and how it does. So these are the 4 questions, and then we can arrange them according to time domain. So who does it is the subject who is holding it, at which condition, so that particular condition is the next spheres, and then what it does, and then how it does. Because the smallest and the fastest one would determine the critical intricate features of the waveforms. So that's how figure 2.5b is very, very, very important, because first time you see the real world information, you can convert it into a nested sphere. So somebody is talking, you can immediately convert it, and then you can change it, and you can modify it, and you can send it. And why we are going for nested spheres? Because we can implement a hardware where oscillators are there, and we can check and verify our hypothesis is correct or not. In fact, all these we have got experimentally first, and then we try to realize it. Now we come to the page 35. In page 35, we have extension of figure 2.5 in figure 2.6. Basically, figure 2.6 and figure 2.5 are the same. Here, we have given certain situations where in a complex scenario, how your algorithm would work. So while building up the algorithm, we faced several problems, and then we have noted them one by one, so that you can support. Okay, so so you can build it. So I'm not discussing figure 2.6 much, because it is the same. We are trying to take a block form. So so this nested spheres, one after another, it becomes time crystal. So what is time crystal? Time crystal is defined and explained in figure 2.7. So figure 2.7a, if you look at it, if some events are happening periodically, you have a sinusoidal wave, and you disturb the system for a certain time, the sinusoidal wave stops, and then a new kind of sinusoidal wave propagates, and then the original signal comes back. The new signal, a post disturbance, the new clock that is coming, that is actually the unit cell. So if I see an oscillator, that is not a time crystal. But if the oscillator is disturbed, and then you find a new frequencies by which you have disturbed, not that one. If someone a tuning form of say 70 hertz is vibrating, and I disturb it, and then it starts disturb it with 10 hertz, and it starts vibrating at 10 hertz, then we will not call it time crystal. It should be, say, 1.001 hertz, which is not any way related to the disturbance that I caused. And that is coming purely from the internal system. So it was internally embedded in the natural vibration of the system. And it broke the symmetry to a domain which I cannot define using the perturbation effect. Then that is the time crystal. So here, in figure 2.7a, you can see that there is an input phase and output phase. So what happens is, suppose you disturb a system, after a certain time it comes back. But when it comes back, suppose a waveform is there, and then it's 1 second, and then after 1 second it will come there, and you disturb it. So after 1 second, it will come back again here, same phase, the original system. Now you can, if you perturb, it can start coming back to the original system at the same time, before or after. That is actually has been explained in figure 2.7a. So if you come early, what will happen? If you come later, what will happen? All these kind of things. Once you know this, you understand that what you get is basically a situation where you have a cylinder, and then you start a cylinder. One part of the circle of the cylinder is the starting point, and you go, and then you can reach other part of the cylinder, same point, or earlier or later. And then one cylinder can trigger another cylinder, and that cylinder can trigger another cylinder. Then we come to the most interesting concept in this book, is Meander flower garden. It was not discovered by us. Meander flower garden, this idea came in the 1990s. Those people who are working on time crystal research, they came up. And then that is very important here. And CD, figure 2.7c, 2.7d, and 2.7e is actually the key fundamental part of this book, how we represent human brain. So what happens is, when you perturb a system and it comes back, then it can come back as a coupled clock, many different geometries that is actually listed. And it looks like a meander flower. So that's why it's called a meander flower garden. So because a garden has many different kind of flowers, so you see that the coupled clocks that are naturally generated in the system, they look different. So figure 2.7c. Now how much time actually is required to recover, based on that, these kind of things happen. Now what can happen is, you can have a system where you have multiple different gardens, and those gardens come together, they share the flowers, and then those shared flowers, the petals come in and then create a new kind of flowers which never existed in those gardens, and then you create a virtual unique garden. That is the artificial brain, that is the human brain with respect to time crystal. So figure 2.7e is the artificial brain in terms of time crystal. So we call it garden of gardens. Okay. So now we come to figure 2.8. In the figure 2.8, we have explained different dimensions. Now, what do we do? So suppose we have to build a sensor, and that sensor would actually acquire all kind of different kind of dynamics. So Fourier transform won't work. 2.7e, we have listed 10 parameters that we cannot get, which we use to do frequency spectrum. And when we come to this kind of new way of doing it, so earlier you used to have one sensory cable. Now you need a bundle, hexagonal close packing, and then packing and packing and packing, and you look at different domains, and then the pattern of patterns, and then different nested clocks and spheres you have to capture directly. So how that those sensors will be really in reality designed, that is actually are shown in figure 2.8. Now we come to a point where we classify that 4-dimension, 8-dimension, and 12-dimension. As I said in tutorial 1, that there will be there will be a journey of 8 dimension to 12 dimension in this book, because in the string theory you had 8 dimension octonions and then 4 dimension quaternions, and you combined them. But what if I create duodecanion directly? That has not been created in the last 200 years. So 12 dimension data, how do we get it? So now, right now, we will get into that discussion. And before that, there is figure 2.9, where we have compared Frank Wilczek from MIT. He has actually revitalized the time crystal, because time crystal research was almost dead in 2000, and Wilczek has revived it. But one problem with Wilczek's person is that one problem is that he thinks that he proposed it, and every media campaigns as if he invented it, and disregard the 30 years of research on time crystal, where Meander Flower Garden, and then many unique universal time crystal, many hard work were done. Those are just totally ignored, which is unfair to hundreds and hundreds of scientists. I have honored them in the book very sincerely. At the same time, if you see the Winfrey time crystal, which was in the 30 years adventure, was actually termed here in this book as Winfrey time crystal, because Winfrey actually compiled in a book. So in his case, there was only one clock, and then Wilczek's case, it was one clock. And for us, we have clock inside a clock inside a clock. It's a beautiful clock architecture. That's why we call it universal time crystal. So that's why it's a huge paradigm shift from their concept. They are limited to one. And if you put many clocks and clock architectures, how the science would change, that we have developed in this book. So figure 2.9 in this sense actually tells you how are we differing. And figure 2.10 is actually quaternion, where you have 3 imaginary worlds and 1 real world. You take elementary arguments, you do information in unit of information. Then you do sensing. When you do sensing, you take those quaternions and put additional 4-dimensional, 4 different kind of dynamics. 4 different kind of dynamics means one kind of dynamics is, say, you move in the x-axis, another dimension is you move in y-axis, another dimension is move in z-axis. They are orthogonal to each other, so no relation. You can have that independently. So now, for sensing, you use octonions, and then decisions are all duodecanions. So this is figure 2.10a. So what you do is, whenever you have a decision, you find the confusions inside. So who does it? A can do, B can do, C can do. Okay, I get a triangle. 10 people can do. Okay, I get 10 shaped geometric object. So basically, we try to classify and then bring it down to the smaller numbers so that we can hold it into the geometric shape. So what we do is in terms of geometry, we write all the arguments. That is in figure 2.10, and then we come to figure 2.11. 2.11 actually explains to you how different dynamics are added. So what happens is, suppose you are moving along the x-axis, y-axis, or z-axis. Okay, so you can have 3 different kind of dynamics. Now, if you have a time, there is another one. We cannot draw it, but you get another dimension. So how to understand these different kind of higher dimensions? It's very difficult, but we have created figure 2.11b, a very beautiful chart where you ask who jumps, and your answer actually tells you what is the higher dimension. For an example, you go to figure 2.11b, you will find one point jumps to another point. So what do you get? Point. You get a straight line. One straight line jumps to another straight line. So if you what do you get? Many infinite number of straight lines. So you get a area. So area means what? Area is a host. Area is a host which can hold infinite number of straight lines. Straight line is a host which can hold infinite number of points. So host is actually that can hold, or that can that can provide conceptual space to lower dimension objects. Okay, one dimension lower. So in this way, start journey. For an example, one surface to another surface, you jump. If you have infinite number of this kind of surfaces, then you get a 3D shape. If you jump one 3D shape to another 3D shape, you get time. You jump one time to another time, okay, and then you have singularity, because you can hold inside the singularity many different kind of jumps, infinite number of jumps. I told you that singularity means you cannot say what is happening over there. Now you have many different kind of singularity pathways. One singularity pathway is like this, just like a sphere. You have a triangle, so 3 singularity pathways. You have another sphere, 4 singularity pathways. So if you have infinite number of these kind of spheres and you want to put it, then you need a universal Euclidean surface. It's a very curved surface, closed surface, a 3D surface, on which you can put those spheres. Okay, each have a path of singularity points. And then if Euclidean volume jumps from one to another, then what you come? You come to the density of primes, because at this point of time, you cannot go beyond the space and time are all exhausted. So you need to go for symmetry. Okay, so you go for structural symmetry, and once structural symmetry actually finishes, then you go for prime. Why? Because you have different kind of shapes, and you know the ratios, and you know the density of primes, which actually gives rise to different kind of geometric shapes. And another thing, important thing that I told many times, is that when you go to the geometry and you want to explain everything in the universe in terms of geometric shape, then you have to forget about all other aspects, because your control is decreased, because primes, symmetry of integers, allowed space restrictions, temporal restrictions of the primes, restrictions of the integers, all this kind of number system theory and all these kind of things start restricting you what you can do with it. So dimension 9, 10, 11, 12 is actually like that. And then the highest dimension is the first prime metric. We will describe that in the chapter 3. So this is figure 2.11. It gives you the idea of higher dimensions. Figure 2.12 is actually a comparison between Turing machine and geometric musical language. In geometric musical language, you write algorithm. Here you don't write algorithm. You arrange the geometric shapes. How do you arrange the geometric shapes? That we will describe in the chapter 3. Not necessary here. But that becomes analogous to the algorithm. So how do you prepare this kind of architecture of confusion? Architecture of singularity points is the architecture of confusion. This architecture of confusion is the solution of the problem. You see, there is a one-to-one correspondence with the philosophy that the Hindu monks used to use for thousands of years to make decision, not on relying on facts, but on the confusions, building this kind of thing. That actually entire philosophy, the way we got experimentally, is summarized in figure 2.13. So in figure 2.13, how do you prepare a non-argument? What is the drive? Drive is to regenerate this structural symmetry. See the beauty? When you come to geometry structures of representing information, then your drive is not human will anymore. It's just geometric constants of the primes, pattern of the primes, and they try to regenerate the symmetries and try to make it more symmetric, and then other things. So that kind of drive. So there, E pi phi symmetry is there, which will come. E is actually 2.73, pi is 3.14, and phi is golden ratio. So these three have a unique quadratic relationship, E square plus phi square equal to pi square. So this relationship we published in 2016, we discovered it in the neuron while studying tubulin protein, microtubule, and the bundle, the microtubule bundle inside the neuron. and then we found that the resonance frequencies, electrical resonance frequencies, magnetic resonance, electrical resonance frequencies, all ratio of the electrical resonance frequencies are E, ratio of the magnetic resonance frequencies are phi, and then ratio of the mechanical resonance frequencies are pi. And then if you when E square plus phi square equal to pi square, basically all three kind of resonances are integrated into one fashion, and then that actually drives integrates the time crystals, because time crystal means different time domain. How can you realize different time domains with, say, ionic conduction? It's millisecond, finish. Dipolar conduction, you say electromagnetic resonance induced dipolar interactions. It's a microsecond or nanosecond time domain, finished. And then you need thermal. So thermal, then soliton and other factors would come in. Then you need orbital interactions, then quantum will come in. So all these kinds of different time domain you need to build to create an architecture of time. So if you say that only one component is responsible for human consciousness or artificial brain, or one component is, no. So here, filtering and then non-argumentative time crystal, how do you build? Everything we have summarized for entire book. So wherever you see this kind of chart, spherical chart, is actually, it's a summary of entire book. So what you will get. So that's figure 2.13. And then we come to figure 2.14 is factual information theory. Whatever I have told you, that there is noise harvesting, E square plus phi square plus pi square is equal to, actually it helps in harvesting noise, because you need to use the thermal, you need to use the entire electromagnetic resonance frequency band, entire mechanical resonance frequency band, another entire entire electric resonance frequency band, and a magnetic, all kind of resonances that can happen. Just you have only one goal, that whatever the artificial brain we want to make, I want to have time crystals or the time spheres whose diameter could be the time, or the perimeter could be the time, and I want to go smallest time to the largest time. Say my atoms are vibrating now, say molecules in my proteins are vibrating, say with the photonic 10 to the 14 hertz or something like that, 10 to the 13 hertz, 12 hertz, and then my conscious experience is in seconds. So it's a huge 10 to the power 22, 10 to the power 24 order of time gap differences there, and we need to integrate all of them together. So that is all about fractal information theory. That's why we want to go inside and inside and inside and inside and inside and inside. So that is the key thing on the paper. So phase prime metric or pattern of primes that we'll describe in the next tutorial. That is there, a drive is there, uncertainty comes in, quantification is there, and the new system points are born. So two clocks are there, they are interacting, and then a new clock is born. So that is a new system point is also born. So how they are born is also described in this chapter in some of the figures you can find. So all those are summarized. There is nothing outside of this particular chart. Okay, so that is figure 2.14, and then we come to figure 2.15. This is also another chart, geometric musical language. So basically in this language you already know everything. It has only one letter, that is circle, one event, that is a clock, only one variable, that is integer. There is no reduction, no rejection of choices, no central control, no past, present, future, no classical point. So all these key features. Clock means it's a memory. Clock means it's a decision making. So you're running a clock, that's a memory. And then you are running a clock, you're passing a singularity once, you are making a decision. So all these key features, how geometric musical language provides, is summarized here. So in this figure 2.15. So 2.15, 2.14, 2.13, all these are charts. They are same basically fundamentally, but we have isolated them and then represented to you, so that you just look at this chart and then you immediately grasp what everything is all about, because there will be nothing beyond that one. Okay, so in the conclusion we go for Russell paradox and higher order logic in a geometric language. So 1 plus 1 equal to 2, with 15 geometric shapes and 15 primes with the ratios, we will be able to represent everything that is happening in the universe in terms of those geometric shapes. So that is a big change, because until now you have been doing 0, 1, 0, 1 and representing everything that was there in the universe. Now you will have 15 geometric steps and you will represent everything in there. And then you will have a clock, and then you go for 3D clock architecture. And then for 3D clock architecture, you will, those clocks will rotate, all those will rotate, and then one clock is there, and then another clock is there. They are rotating. There is a meander flower, and then another part, another meander flower, another meander flower. The 3D clock architecture is just like a garden of meander flowers. But that concept came in the 1990s. That is the old concept. But universal time crystal, where you put clock inside a clock, inside a clock, inside a clock, inside a clock, that is purely our concept, and that we have exclusively developed in our research here. So that's the end of this chapter, and then the end of this tutorial. I will come back with the chapter 3, and I will explain how we can understand phase prime metric, or chapter 3. So this was all about the language, and a very brief summary of all the figures. Thank you.